Have you ever wondered what lies beyond the stars? What if I told you that the universe, the vast expanse of everything we know and don't know, is expanding? Yes, you heard it right. The universe is getting bigger every second. But how? Let's dive in. In the early 20th century, astronomer Edwin Hubble made a startling discovery. He found that galaxies are moving away from us, and the farther they are, the faster they're moving. This phenomenon, known as the Hubble's law, was the first evidence of the expansion of the universe. Observations of the cosmic microwave background from the European Planck Space Observatory suggest that the universe is expanding at the rate of about 67.4 kilometers per second per megaparsec. A megaparsec, MPC, is a unit of distance used in astronomy, especially when measuring the vast distances between galaxies. It is equal to 1 million parsecs. To give you some context, a parsec is a unit of length used to measure large distances to astronomical objects outside the solar system. It's approximately equal to 3.26 light-years or 206,265 astronomical units, AU, which is about 30.9 trillion kilometers or 19.2 trillion miles. So if 1 parsec is about 3.26 light-years, then 1 megaparsec, being 1 million parsecs, is about 3.26 million light-years away. To convert 1 megaparsec to kilometers, you'll need to multiply 3.26 million light-years, which represents 1 megaparsec, per 30.9 trillion kilometers, which represents 1 parsec or around 3.26 light-years. And the result is the staggering amount of 100 quintillion 734 quadrillion kilometers. This means the universe is expanding at a rate of 67.4 kilometers per second per megaparsec, or 6 sextillion 789 quintillion 471 quadrillion 600 trillion kilometers per second. These large units of measurement, like the megaparsec, are essential in astronomy because the distances in space are so vast that using smaller units like kilometers or miles would result in incredibly large and unwieldy numbers. On the other hand, measurements from the Hubble Space Telescope indicate that the expansion rate for the nearby universe is just under 70 kilometers per second per megaparsec. More recent data from the Hubble Space Telescope even suggests a rate of 74 kilometers, 46 miles per second per megaparsec. This discrepancy between the different measurements is a fascinating puzzle for cosmologists. It could suggest that there may be something woven into the fabric of space that we don't yet understand. Resolving this discrepancy might require new physics, or it could be a result of measurement errors between the two different methods used to determine the rate of expansion of space. The James Webb Space Telescope has been used to cross-check Hubble's results, and it confirmed that the Hubble telescope's keen eye was right all along. So, the exact rate at which the universe is expanding is still a topic of ongoing research and debate in the scientific community. At this moment, you might be thinking, how is the universe expanding faster than the speed of light? The universe expansion exceeding the speed of light might seem counterintuitive, especially considering that nothing can move faster than light in a vacuum, according to Einstein's theory of relativity. However, it's crucial to understand that this rule applies to objects moving through space, not to the expansion of space itself. The universe expansion is often described using the analogy of a balloon. Imagine a balloon with dots on it, representing galaxies. As the balloon inflates, the dots move away from each other. The farther apart the dots are, the faster they move away from each other. This is similar to how galaxies in our universe are moving apart due to the expansion of space. Now let's address the speed of light. The speed limit set by light applies to the motion of objects within space, but there's no speed limit to how fast space itself can expand. So when we say the universe is expanding faster than the speed of light, we mean that the space between very distant galaxies is increasing so rapidly that the light from those galaxies may never reach us. Moreover, the universe expansion is accelerating due to a mysterious force known as dark energy. This acceleration can cause very distant galaxies to apparently move away from us faster than the speed of light. So, while it might seem like a violation of the speed of light rule, the universe's faster-than-light expansion is actually a result of space itself expanding, not galaxies moving through space. But why is the universe expanding? To answer that, we need to go back in time, about 13.8 billion years, to the moment of the Big Bang. The Big Bang wasn't an explosion in space, but an explosion of space. The universe was born with the Big Bang as an unimaginably hot, dense point. This marked the beginning of the universe and its expansion. When the universe was just about 10 to the power of -34 of a second old, it experienced an incredible burst of expansion known as inflation. During this period, the universe doubled in size at least 90 times, going from subatomic size to golf ball sized almost instantaneously. In a billionth of a trillionth of a trillionth of a second, the universe grew by a factor of 10 to the power of 26, comparable to a single bacteria expanding to the size of the Milky Way. As space expanded, the universe cooled and matter formed. 1 second after the Big Bang, the universe was filled with neutrons, protons, electrons, anti-electrons, photons, and neutrinos. During the first 3 minutes of the universe, the light elements were born during a process known as Big Bang nucleosynthesis. For the first 380,000 years or so, the universe was essentially too hot for light to shine. Roughly 380,000 years after the Big Bang, matter cooled enough for atoms to form during the era of recombination, resulting in a transparent, electrically neutral gas. This set loose the initial flash of light created during the Big Bang, which is detectable today as cosmic microwave background radiation. So, what is the cosmic microwave background radiation? The cosmic microwave background, also known as CMBR, is a type of radiation that fills all space in the observable universe. It's a remnant from the early universe and provides an important source of data on the primordial universe. The accidental discovery of the CMB in 1965 by American radio astronomers Arno Penzias and Robert Wilson was the culmination of work initiated in the 1940s. The CMB is landmark evidence of the Big Bang theory for the origin of the universe. Although the expansion of the universe gradually slowed down as the matter in the universe pulled on itself via gravity, about 5 or 6 billion years after the Big Bang, a mysterious force now called dark energy began speeding up the expansion of the universe again. This phenomenon continues today. So, the expansion of the universe after the Big Bang involves a series of complex and intriguing processes, from the initial inflation to the formation of matter, and finally to the accelerated expansion driven by dark energy. At this point, you might be wondering about what is dark energy. Well, dark energy is a hypothetical form of energy that is proposed by physicists to explain why the universe is not just expanding, but is doing so at an accelerating rate. It's an unknown form of energy that affects the universe on the largest scales. Its primary effect is to drive the accelerating expansion of the universe. Think of dark energy as the evil counterpart to gravity, an anti-gravity force providing a negative pressure that fills the universe and stretches the very fabric of space-time. As it does so, dark energy drives cosmic objects apart at an increasingly rapid rate, rather than drawing them together as gravity does. Dark energy is relatively uniform in time and space and is gravitationally repulsive, not attractive within the volume it occupies. It's believed to contribute about 68% of the total energy in the present-day observable universe. The exact nature of dark energy remains unknown, but there are a few theories. The main candidates are a cosmological constant, representing a constant energy density filling space homogeneously, and scalar fields, dynamic quantities having energy densities that vary in time and space, such as quintessence or moduli. A cosmological constant would remain constant across time and space, while scalar fields can vary. Now, why does dark energy accelerate the expansion of the universe? Because this energy is a property of space itself, it would not be diluted as space expands. As more space comes into existence, more of this energy of space would appear, thereby causing accelerated expansion. These sorts of disturbances are inevitable due to the uneven distribution of matter throughout the universe. If the density of dark energy remains constant over time, our universe will continue its current accelerating expansion indefinitely. This means that the universe will keep expanding at an ever-increasing rate, and structures that are not already gravitationally bound will eventually fly apart. In this scenario, the Earth and the Milky Way would remain undisturbed, while the rest of the universe appears to recede from us. However, if the density of dark energy increases over time, the universe could end in a big rip. In this scenario, the dark energy density would grow to infinity in a finite amount of time, and its gravitational repulsion would become so strong that it would tear apart all objects in the universe, from galaxies and stars down to atoms. So, while we don't know exactly what dark energy is, we do know that it exists. It's making the universe expand at an accelerating rate, and it's one of the biggest mysteries in cosmology today. The universe is a vast, dynamic, and ever-evolving entity. Its expansion, driven by the Big Bang and accelerated by dark energy, is a testament to the incredible forces at play in the cosmos. The exact rate of this expansion and the nature of dark energy remain some of the most intriguing mysteries in cosmology. As we continue to observe and study the universe, we are constantly challenged to revise our understanding of the fundamental laws of physics. The universe's faster-than-light expansion, the Big Bang, the formation of matter, and the concept of dark energy all serve as humbling reminders of the grandeur and complexity of the cosmos. As we delve deeper into these mysteries, we inch closer to understanding our place in this vast expanse. The journey of discovery continues, fueled by human curiosity and our quest for knowledge.